We will now proceed with presentations by Ontario Power Generation and the Canadian Nuclear Safety Commission pertaining to the subject of updates to the Geoscientific Verification Plan. The panel will hear both presentations before proceeding with its questions. We will wait to hear from Natural Resources Canada until after the panel has asked its questions of OPG and CNSC, because Natural Resources Canada's presentation covers a more broad range of topics. I would now like to call on Ontario Power Generation to begin their presentation, which is PMD 14-P1.1F. Ms. Swamy, the floor is yours.
Lori Swamy for the record. Good morning, Dr. Swanson and members of the panel. This morning, Mr. Mark Jensen will provide the presentation on the Geoscientific Verification Plan. Mr. Jensen is the director of the DGR Geoscience and Research Program at the Nuclear Waste Management Organization. Mr. Jensen.
Thank you and good morning. For the record, my name is Mark Jensen. I'm joined this morning by Dr. Joe Carvalho, principal from Golder Associates, who was involved in the development of the geotechnical component of the revised Geoscientific Verification Plan. The purpose of the presentation this morning is to describe a revised Geoscientific Verification Plan that addresses Information Request EIS 12-511. In particular, it describes material changes to the Geoscientific Verification Plan that involve the addition of planned geotechnical activities related to safe construction practice and engineering design verification. The main elements of the presentation include the nature of the information request, EIS 12-511, the Geoscientific Verification Plan approach, enhanced geotechnical verification activities, the subsurface excavation design and construction approach, including trigger values, and a summary. Following the October 2013 presentation of the Geoscientific Verification Plan at the Joint Review Panel hearing and discussion of additional geotechnical information to support DGR construction and design verification activities, information request EIS 12-511 was received. The information request asked OPG to provide an updated geoscientific verification plan that included more details concerning specific methods, timing, and the sequencing of sampling, as well as how OPG will develop triggers for changes to engineering design and benchmarks for verification of the safety case. The revised 2014 Geoscientific Verification Plan now incorporates both geoscience safety case and geotechnical construction activities. The original geoscience-related activities remain materially unchanged. The increased scope in the Geoscientific Verification Plan describes best international rock engineering practice as relevant to safe construction practice and design verification during construction. The geotechnical monitoring and investigations proposed significantly extend activities associated with geomechanics, in particular excavated rock mass response during construction. Proposed rock mass response monitoring activities will be conducted real-time in both the ventilation and main shafts during construction. Reasoned geotechnical trigger values have been established to gauge whether the rock mass response observed during construction is within expected ranges and engineering design tolerances. These geotechnical trigger values were included in the OPG response to information request EIS 12-511. As was demonstrated and found best practice in the surface-based investigations, detailed test plans will be developed prior to initiation of any activities. This approach assures, first, that the methods and techniques applied are consistent with best demonstrated experience at the time of construction. Second, that the test plans are available in a timely manner to provide technical specification of services and monitoring instrumentation for implementation. Third, that relevant geotechnical trigger values for excavation safety and design verification are established. And fourth, that there is compliance with the DGR project quality plan. The planning and timing of all activities is directly linked to specific information requirements, whether they be real-time assessment of excavation safety or geotechnical design verification, or the verification of site-specific characteristics to verify the DGR safety case in support of a future operating license application. In other words, the timing and scheduling of activities is established to coincide with the need for the information. It is important to recognize that the geoscientific verification plan may evolve as the final engineering design is developed to ensure consistency with improved Canadian or international underground construction experience and to respond to future regulatory comments and/or guidance. In a sense, the plan is a living document, the revision of which would be subject to regulatory oversight. Slide 5 and the accompanying table provide an overview of the revised geoscientific verification plan. The parameters and site attributes that the geoscientific verification plan is designed to address are listed on the left-hand side of the table. The center and right-hand columns denote activities for the geoscience or safety case and the new geotechnical or construction components of the plan within the shafts and lateral development. The original safety case related activities were broad in scope and specifically proposed to support verification of the DGR safety case. These activities focused, for example, on the verification of parameters most influencing DGR safety assessment, obtaining site-specific geoscience evidence to test and reassess the understanding of geosphere stability, and confirming geomechanical conditions governing the assessment of long-term DGR opening stability. These safety case-related activities are shown by the open green diamonds and the blue triangles in the center column. Within the revised 2014 Geoscientific Verification Plan, the planned geotechnical related activities associated with construction are now described. This is shown in the right-hand construction column of the table, with the small blue circles representing new activities and the large circles increased activity over the original plan. These activities specifically address the requirement to confirm rock mass properties and response during construction. The increased scope within the geoscientific verification plan includes in situ stress measurements using the United States Bureau of Mines overcoring technique within the vertical and lateral development, an under excavation test which has been repositioned to the DGR Geoscience Room within the Coburg Formation to obtain improved estimates of in situ stress orientation and magnitude. Geotechnical instrumentation installation. There is extensive installation of multi-point borehole extensometers and stress cell arrays to monitor rock mass displacement and opening stability. Parameter upscaling tests, the use of excavation response, and large diameter samples to verify expected rock mass properties. Pillar stability integrity, including the instrumentation of emplacement room pillars to monitor and demonstrate pillar structural integrity, and groundwater inflow as relevant to safe construction practice. It should be noted that where properties and attributes are of interest to both geoscience and geotechnical work programs, the proposed methods and techniques for characterization are now described in the geotechnical section of the Geoscientific Verification Plan. The location of planned geotechnical or construction-related activities within the main and ventilation shafts are shown in slide 6. Geologic mapping will be performed to gather information with regard to lithology and geologic structure. The mapping would include both LiDAR and photogrammetric imagery of the excavated walls. Geomechanical properties, in particular upscaling Anisotropy will be assessed through the observation of rock mass displacements and stress change within the extensometer instrument arrays at 7 locations as shown in the figure. Groundwater ingress in the upper 200 meters of the excavated shaft will be monitored to assess grout curtain effectiveness and to ensure manageable construction conditions are achieved. Inflow rates less than 3 liters per second. Groundwater inflow is not anticipated below 200 meters with the exception of the confined saline aquifers at the top of the Salina A1 member and the Guelph Formation, each horizon approximately 4 meters thick. Finally, in situ stress measurements will be obtained in vertical boreholes extended beyond the working face in the main shaft using the overcoring technique, the selection and justification of which is described in the geoscientific verification plan. Slide 7 illustrates the location of the new geotechnical or construction-related activities within the lateral repository development. All excavated openings will be geologically mapped, which will include the collection of LiDAR and photogrammetric imagery. The LiDAR profiling will be kept capable of detecting rock mass displacements of millimeter scale through the comparison of subsequent surveys using benchmark monuments. Geomechanical properties will be confirmed through characterization of rock mass response, such that upscaled values are obtained for confirmation of design properties. In addition, laboratory strength testing will be performed on large diameter samples to characterize anisotropy. Excavation response will be monitored through the installation of multi-point borehole extensometers and stress cell arrays within the crown and the floor of each emplacement room. Although hydrogeologic conditions make it extremely unlikely, evidence of groundwater seepage will be recorded during mapping and, if possible, samples gathered for analysis. Studies to monitor pillar response to excavation will be performed at 3 locations, as shown in the figure. The intent is to confirm pillar integrity given they have been purposefully designed to be unconditionally stable. Finally, in situ stress measurements will be made within the Sherman Fall Formation on the down ramps to the shaft bottoms by USBM overcoring. In addition to the performance of a large-scale under-excavation test now repositioned from the base of the main shaft to the geoscience room. The observation method is a practical and internationally accepted approach for subsurface rock engineering design and construction. The approach is designed to reduce the risk of engineering decisions given possible uncertainties in subsurface conditions. This approach, as described within Eurocode 7, has been applied by other international radioactive waste management organizations. Application requires consideration and adaptation of an engineered design to site-specific geotechnical conditions. Implementation of the observation method within the DGR project requires that acceptable limits of rock mass behavior for site-specific engineering designs be established. A plan for monitoring is devised to yield reliable information on parameters able to reveal whether behavior lies within accepted design limits. The monitoring plan requires response time sufficiently rapid to allow for analysis and confirmation of acceptable design conditions during the construction cycle. To achieve this, trigger values are developed to allow an objective reassessment of rock mass response parameters most influencing excavated opening safety and shaft lateral engineering design. This approach allows for design verification during construction with the possibility for design revision or adaptation in the event that conservatively estimated rock mass response assumed in the design is observed to be materially different than expected. The purpose of trigger values is to provide an indication of a deviation in expected rock mass response from that considered in the DGR design basis. The trigger values are purposely selected and set for rock mass parameters and conditions that govern opening stability and safety. and information needs required to verify the DGR engineered design. As described in Table 4 of the of the response to information request EIS 12511, an example of a geotechnical trigger value during shaft excavation would be that rock mass deformation measurements should not exceed 5% of predicted before casting of the concrete liner. Another is in situ stress in the lateral development, such that the maximum principal stress not exceed 35 megapascals and orientation be within 30 degrees of expected. This is in contrast to the geoscience or safety case program, in which assessment of collected data assessment of collected data requires it to be considered as a whole or system. This said, if a fault with 0.5 meters displacement and high groundwater inflows were unexpectedly intersected at the repository horizon, this would represent a reportable event to the CNSC and would require reassessment of the safety case. As noted, the geotechnical trigger values are established on a conservative design basis. For example, the rock mass strength is lower than actually expected, and thus are unlikely to be exceeded. It is important to recognize that each trigger parameter represents only one indication of rock mass behavior. Proper interpretation and assessment of geotechnical trigger value trending and possible exceedance requires a holistic approach in which coincidence between multiple parameters and evidence are considered to assess impact on shaft or repository design, and if required, any mitigating activities. As discussed, trigger values may require further refinement at the final stage of DGR design, in part to ensure consistency with contractor equipment and construction methods. This would be documented within the detailed test plans that would be subject to regulatory oversight. In summary, the Geoscience Verification Plan has been revised to include planned geotechnical activities associated with the assessment and monitoring of excavated opening stability, construction safety, and design verification. The geoscience or safety case component of the Geoscientific Verification Plan originally presented remains materially unchanged. The plan represents a framework for subsurface geoscience and geotechnical activities to be conducted during DGR construction. The timing and scheduling of activities coincides with requirements for the data need, whether this be real-time monitoring to assess opening stability and design verification, or confirmation of site attributes underpinning the DGR safety case. As has been practiced in the past, detailed test plans will be developed for individual activities prior to their initiation. Such test plans will establish and document trigger values to be observed during excavation monitoring and design verification. Information and data gathered during geoscientific verification activities will be included in a future safety assessment to reveal impacts, if any, on DGR performance. This information would be included in an operating license application. The Geoscientific Verification Plan is subject to change in terms of addressing the final detailed repository design and/or regulatory comments and guidance. Any modification or revision of the plan would occur within regulatory oversight. This completes the presentation of the Geoscientific Verification Plan. We would be glad to answer any questions. Thank you.
Thank you, Mr. Jensen.